Hi, good afternoon, everyone, and welcome to our webinar series called Experts Speak, sponsored by DataMites in association with IABAC, the International Association for Business Analytics and Certification. Let me give you a brief about the speaker for today, Mr. Akshit. He's a data scientist with over 7 years of experience specializing in business intelligence, machine learning, and artificial intelligence. He is passionate about creating top-tier architectural solutions for diverse challenges in the field of data science. He's also proficient in crafting intricate data models and has cultivated a robust portfolio showcasing his AI experiences across various domains. His journey started from handling small, agile teams to spearheading pivotal roles in large-scale projects involving numerous stakeholders. He also thrives in a collaborative environment to foster cross-functional partnerships to leverage a large global network for impactful results. And today he'll be covering the topic on deep learning model introspection. And one request to all the participants, please post the queries in the chat and we'll present it to the speaker at the end of the session. Over to you, Akshit.
Thanks, Ram, for the beautiful introduction. And greetings, fellow explorers of AI and human experience. So, today we embark on a quest to capture one of the most captivating facets of human perception, that is surprise. And we will also explore how deep learning can empower machines to identify images that breaks from expectations, spark curiosity, and challenge our understanding of visual world. So before going into deep, so I will just like to introduce why deep learning model introspection is essential. So for those who are new to this, so let's imagine driving a car blindfolded. What will happen? You follow instruction, feel the turns, and sense the speed, but you lack the crucial element, that is sight. This is akin to the current state of many deep learning models. We feed them data, they provide us output, but understanding their internal reasoning remains a blurry landscape. This is where deep learning model introspection shines its light. So what happens in model introspection? So we are just unveiling the black box. Deep learning model, particularly intricate one like neural networks that can be opaque. Their layer perform complex calculation that can often defy easy interpretation. Introspection techniques peel back this curtain and allowing us to understand decision making. Why did this model make a certain prediction? Which feature influenced its judgment? Introspections offer insights into the reasoning behind the output, building trust, and identifying the potential biases. Debug and diagnose. Is the model struggling with specific data points? Are internal inefficiencies hindering its performance? There are many more aspects to that. And one of the aspect is accuracy. But beyond accuracy, while model accuracy is paramount, it's just one piece of puzzle. Introspection allows us to delve deeper. So it unlocks potential applications like the benefit of deep learning model introspection extend far beyond model debugging and understanding. It opens door to exciting possibilities like personalized learning, medical diagnosis and treatment, explainable AI in critical domains. Deep learning model introspection is not just a technical challenge, it's a key step towards truly intelligent and trustworthy AI systems. By peering into the inner working of these models, we unlock their full potentials to learn, reason, and explain, paving the way for future where AI seamlessly integrates with our lives guided by clarity and insights. So let's go into our slide number 1. What is our goal? To develop a framework using deep learning to detect surprising images based on their visual content. So what does it mean when I telling you about surprising images? So it can be subjective, it can be relative, and it depends on the personal experience. So we define surprise images are those that significantly deviate from the distribution of known training images. And what we do, there are four things that are required to identify that. One thing is that you should have your own training pipeline so that you can train a model. Then you can implement many feature extraction techniques like LRP, Shapley, global average pooling. There are many methods that you can use to extract feature, and even you can customize your own feature extraction process. And the third step is measuring surprise. Either you can use Euclidean distance, cosine similarity, or any other metrics so that you can identify the distance between your trained features as well as your unseen features that is new to the model. And quantifying the unexpected. Higher score, higher surprise images with large averages distance are considered more surprising as compared to the training data. So coming to our thing that I am going to show you today, what dataset I have chosen. I have chosen Berkeley 100K dataset, which has 10 tasks to evaluate the exciting process of image recognition algorithm on autonomous driving. The dataset possesses of geographical, environmental, and weatherly diversity, which is useful for training models that are less likely to be surprised by new conditions. What does this mean? That it is a hypothesis for now that the 100K dataset that we will be training our model will have all the possibility of a vehicle or pedestrian or any objects that lie on the road. So we use YOLO V5 as our model, but it's a custom trained YOLO V5 model that we trained on 100K images. And you can find the link in this PPT to the training pipeline as well as the dataset paper. And feature extraction, we did our own feature extraction. You can use your own custom feature extraction techniques uh, to extract the features from the train as well as test images. Then what you will do, you will just take the distance between the features and the test features and the training features, and then you will get to know some score that you will treat it as a surprise score. Okay, so for example, what I'm showing here, this is one of the images on which the model was trained. And you can see these are some European conditions that are present in the Berkeley dataset. So you can see that on the training dataset, which is obvious, the model is performing good. Large vehicle is identified as large vehicle, passenger car is identified as passenger car. But what happened when we will introduced new distribution of dataset to the existing model, which was trained on the European condition, which was Berkeley dataset. So, for example, this is some Asian images captured in Asia. So, for example, for this image, the model performs extremely well. The passenger car, I can enlarge this image. So the passenger car was getting detected. It's auto, but model is treating as passenger car. That's fine. And car was detecting as car, and everything is as expected. But what happens to this condition? So you will see the model is confused, not able to detect all the objects in this image. Why this happened? So what does this mean? We can relate that this kind of images the model has not seen while getting trained, right? So there is a method that you can identify that your model is performing well or not well by using IOU, mean average precision, and any other metrics. But for that, you need ground truth. So what will happen in IOU? You will take the ground truth and take the prediction, then calculate the area which is overlapping, right? But imagine if there are, you cannot tell that these are the images which is going to confuse the model. There can be any images and you need to identify the images and then write the ground truth, means annotate the images with ground truth. So that is very difficult, right? To having the ground truth of thousands of images, it's is itself a very this is very expensive. You will require many resources, levelers, annotation software, so many things is required. But what if I will tell you without the ground truth that these are the images that your model will be getting confused or your model will be surprised. So this is what I tried to do here. So just I took the distance between the training features and the unseen images feature and just calculated the Euclidean distance between them. One to many Euclidean distance for each of the feature. So to show you how I got these images, so just let me share one snippet of the code. I think my this image came from this notebook. So what we are doing, we are just extracting the features in a .pt file, and then we are reading this. And same we will do with the unseen set of images, which were the ASEAN images, and we'll try to extract the features. So same thing we are doing here. We are giving the test images as well as model to give you the essence that what our model is. So this is our custom trained model based on Yellow 5 architecture. So which works well. It was trained on a large amount of data sets. So now what I'm going to do here, just I will calculate the distance between the test features, that the training features, we have saved it as a .pt file, and now we have extracted the test features, and just we will calculate surprise. And calculate surprise is nothing, it is just the Euclidean distance between the training feature and test features. And you can use any other metrics as well. And just we have a uh, the unseen dataset was of size 2704, and the maximum surprise score we got as 13.88, and the minimum surprise score we got as 1.8. So what we did here, so we try to identify the images where the model is performing good and to test our surprise scores as well. So for that, what I given, just I taken the threshold of 1.85 and identified one images which was on index 155, and try to identify that whether the model is performing good on or bad on this. So array 155, the image should perform, the model should perform well because it's kind of image which is similar to the model which on which the model was getting trained. So for example, to show you, so this one was the images. So we knew already that model is going to perform well without using the ground truth. For example, let's say another sets of images. Let's say we have given threshold 2 and just ran that, and let's get the indices of low surprises score. So these are the images where model is performing very extremely well. So for example, if we will take 13, we already know that model will perform well on this kind of images. So let's plot it as well and do the inference on this image. So model is performing extremely well. How you know that? So just I will going to expand this image. And you can see that all the objects are getting detected correctly. And this we came to know without using the ground truth. So what will happen? Before that, I will show you some bad examples as well. So let this image we got when we used threshold equals to 13, and you got to know that this images and the model performed extremely bad while predicting this image. So if you can see here, that I had already shown you in the slide. So all the objects got missed. So let's further investigate some more images. Let's give the threshold as 10 and let's identify some more bad images index. So 455 is the one. We already know that this is the image which model has not seen and model will perform bad. So let's see further. First, let's see what image is this. So this kind of images model fails actually, and let's inference it as well. So you can see a lot of the objects are getting missed. So we already know that how to identify the images the model has not seen. So this is one of the model introspection techniques that user can implement. This is nothing new that I have invented. So this is some of the techniques that a developer should know to investigate their model. and to work on efficiently both on the time as well as on the cost side. So let me share my screen again. So what will be the applications for this example? So you can go beyond outlier detection, identify subtle anomalies that might be signify emerging trends or hidden trends, or just you can identify the outliers in simple words on which the model is expected to fail, and leveraging surprise score to rank prioritize potential anomalies for further investigation. You can not only use this on vision models, you can use on any deep learning models where you can extract the features, and you can extract the features easily based on your requirement. And also it will reduce the data acquisition cost by focusing on surprising or informative data points to refine the model efficiency. Now, what will happen if your model is performing bad? Then you will train only on those images on which the model is performing bad. So you already know that on which kind of images or similar images the model has not seen, and you will get that images and annotate it and give it to the model, retrain it, and you will understand the score will increase because the model now has seen this kind of images. You can also improve data labeling efficiency by prioritizing challenges or ambiguous example identified by the surprise score. You can also enhance model generalizability by incorporating diverse and unexpected data points. So this is all which I can show you. So I am open to questions. Yeah. And if you wanted to learn more about other introspection techniques and why surprise methods, we have a time, so we can I can explain you that as well. So why surprise matter? Surprise is fundamental cognitive mechanism that derives learning, adaptation, and creativity, and it signals a mismatch between the expectations and reality. So your way of thinking will be changed after seeing that you saw that the MAP, the IU is performing extremely well, but you got to know that on the real world images, your model fails to identify the extreme conditions. So this is some of the thing that you can derive from surprise matters. And coming to feature extractions, there are a lot of papers on that. So you can find GradCam is one of the techniques, integrated gradients, deep dreams, Lime like local model mimic, which whispers explanation trailer to each instance, shape, which is shapely additive explanations, which gives you fairness and dividing credit like a cooperative game. There are other methods like counterfactuals. It will add what if scenario to your pipeline, and it rewinds the decisions to see alternate realities. So there are many methods like one of is most famous one is the activation maximization. You will do reverse engineering and craft the input that trigger specific neurons. So you can go as much deep as you want, and there are you can use attention mechanism. So there are many methods that you can use. So my uh, the entire thing about this was to learn more about the model and why model is taking certain decision that the developer should know. So this is why I chose this topic to discuss here. So I can see some questions. Yeah, I got one question from Sarath. What are the ethical considerations when introspecting deep learning models on sensitive data like healthcare on finance? So definitely you will not get this kind of data as a open source, like you are roaming on the road and you can click the pictures and you can take the prediction. That also is not going to happen and not you will be able to find. You can get this data from radiology.nl. That is a good collection of having the healthcare data. For finance data, it depends who is going to share your data, and there are certain privacy policy to that as well. So you will not get those data easily. Yeah. Anonymous, are there specific industry or use cases where model introspection is important? So it is important ideally in all the industry where you use deep learning. Deep learning is not for predicting it's rain or it will not rain. So when you will go to complex scenarios, then you will identify that model introspection is needed. You cannot stand and you can tell that your model is performing very good and it will outperform the other models, like for example any autonomous driving model which will detect this in Europe, it is not likely to be detected in Bangladesh. So it depends on certain conditions. So you need to be free for the distribution to handle. So this is not that only accuracy matters. That is the reason. How does deep model introspection contribute to improving the transparency and interpretability of deep learning model? So this is one of the example that I showed you. So what will happen? You get to know that to what extent of or to what kind of images your model was not performing well. For example, the examples I showed you in this slide, this was a jam condition and your model has not seen this kind of images earlier. So that is the reason your model is not performing well. Or you can also take inference from here that it's blurred. The objects are not visible with eyes. We know that there are certain objects because we are using our brain, but to a model, it will not identify the features. So for that models, uh, for that images, the model is going to fail. How can model introspection help in identifying and mitigating the biases in deep learning models? So this is what I have answered just now. So you will be biased to your data set, like your training data set and the validation data set, but you don't know the distribution. Either it depends on many things, either it's taken the images or anything is taken in the day situation, night situation, rain situation. So there are a lot of things that you don't know while training. You just got the data set, divided into train, test, and validate, and just train the model and validate it, and you came to know and telling that your MAP is good, your RU is good, your accuracy is good, your model is performing well. But that is not going to be the case. That's why it mitigates biases. The model underperformed in some. There is another question from Frederick. The model underperformed in some datasets and overperformed in the test dataset and trial dataset. Yes, correct. You are correct on this. Uh, because the why it underperformed, because you showed the real world scenarios to the model, and the data set on which it was trained, it was just Berkeley 100K images which are very neat. That was the reason. I have another question, that is this foundation class when okay. Another, why we use Euclidean distance and what kind of metrics we can use. So you can use cosine similarity, or you can use pairwise distance. You can use Manhattan distance. Whatever you want, you can use. Euclidean distance is just a matrix. Uh, is it applicable in convolutional neural network? It is convolutional neural network. Having means we used YOLO V5 as base, and we trained our own model. So I think that are all the questions. Uh,
Yeah, Akshit,
yeah,
we can actually, I mean, I say, because the session was pretty technical in terms of like, you're showing us pieces of code, right? Will you be sharing your PPT with those links so that, can you share it with us so that we can post it to all the participants? Because we are showing some Jupyter notebooks uh, with some Python code, right?
yeah.
So is it something uh, yeah,
Yeah,
specifically?
I can share the PPT. So
Yeah, yeah. I can, at the end of the session, we'll post it to all the speakers, to all the participants. Apart from the questions, right? Can you throw more light on, other kind of use cases where, uh, in which industry are we using this uh, introspection models? And you can ask typical questions also, like, whatever we have may have not got to hear. What are the typical questions people ask in terms of, the ethics, and what are the frameworks, what people need to adhere to, with this? Because artificial intelligence itself is at a very nascent stage, no? And a lot of ethical considerations and frameworks need to be, like, adhered to before, like, incorporating this. Because all this stuff right now, I think people who are using surveillance and mostly sensitive data is what people will be using for this kind of models, right?
Yes, yes, yes. So good question on this. So mostly you can use in autonomous driving, and the most related, closely related is healthcare, because you cannot take a risk. So even if a pedestrian is not getting detected at once, what will happen? So it is very critical, and same in the healthcare domain. So that's why model introspection is needed there. And one of the most asked question that I get usually, that can't we do layer wise? Because what is deep learning? Deep learning is just summation of many layers that has their own activation functions, neurons, and it takes input and gives output to the subsequent layer, and it just a set of layers. So yes, definitely there are other methods as well you can use to identify how which neuron actually got activated you when you got this kind of data, and what was the activation that was used which resulted in a 0 or 1, why it is 0, why it is 1. So there can be lot of questions and that you can investigate as well. So this is one of the question that I got. And definitely, one of the most important thing here is data. So you will not get labeled data. So for those cases also, if you wanted to, you are serious about training your model and you don't have data and you don't have much resources to label it also. So then you need to identify the edge cases where your model is going to fail. So for those cases, you can also use uh, this kind of introspection or other kind of introspection. So it can see some more questions, I think. Are we going to minimize or maximize the score? Yes, we are going to maximize the score by training it again on this set of similar images. What will be our next task? To identify this similar image and get it annotated, and just retrain the model with those images, and we will get a new model, and definitely it will perform good on this kind of similar images. Think around we are good. Then any other questions are welcome. You can post in the chat. So that's good.
Like, yeah, can wait for some questions.
Definitely.
Are there more use cases which you can throw light on, even though if you don't have slides for it also, like, where else can uh, this kind of, deep learning introspection models are being, like, incorporated?
Yeah, this all comes like the methods that I was telling you, like feature importance, activation maximization, counterfactual, say, lime, gap. So these all comes under the umbrella of explainable AI. And it is just opening the black box with diverse tool. This is what I can say about this. And what will happen and why we use this. So to understand a decision making, why did a model make a certain prediction? What feature influenced its judgment? Why a neuron got activated? Introspection offers insights into the reasoning behind the outputs, building and potential biases. So explain you if you want to explain your outcomes to humans in domain like healthcare, finance, explainability. So it is very critical that you have to explain your outcomes to human, how you will do that. So this introspection unlocks why behind the model decision, enabling clear communication and fostering trust. And also, one of the question that I got about the bias detection, for example, a question: are certain groups disproportionately affected by models' output? This answer you can give. So introspection reveals the potentiality biased features for decision-making patterns, allowing mitigation and ethical developments. And you can also use this in transfer learning and knowledge reuse. Can knowledge gleaned from one model to be applied to another? Introspection facilitates the knowledge transfer, improving efficiency and accelerating development. So, unlocking potential applications, the benefits of deep learning model introspection extends far beyond the model debugging and understanding. It opens doors to exciting possibilities like in medical diagnosis and treatment. By understanding how AI models diagnoses diseases, doctor can gain deeper insights and make informed treatment decision. So everywhere explainability is very critical in domains like healthcare, finance, autonomous driving. So always in high stakes field, or for example, financial forecasting, introspection ensures transparency. And what does it do? It just build trust on your model.
Yeah, Akshit. Are we done with the questions, or do we have more
There is
coming?
one more question, that what if we are identifying odd species, how to generate model? Is it applicable? So first thing you will have to do is train your model. For that, you need data for certain wood species. Either it can be a classifier, I think. And what you will do after that, you can take the ultimate layer or the penultimate layer or any layer if you wanted to do the introspection. And then you can extract the feature and do whatever you want to do. And you will be able to do that. It is applicable to all the deep learning models. Can we apply search methods in selecting the models with minimum error? Yes, you can apply this method. There is one more question from Hilary Smaha. In this picture, what will happen if we ask model to recognize the persons, not the car? Is it going to be intensive computing? So if your model is trained for detecting the pedestrian, then you can detect the pedestrian. If your feature or your ground truth doesn't have the pedestrian, then your model will not able to detect. And yes, it will be computation will be required. It depends on how much the data size of train or data size you have. If you have, it is directly proportional to the number of images in your trains data set. I think most of the questions are answered, Ram. So thank you for joining. Thank you.
Yeah, thank you everyone for joining in, and please visit our website at datamites.com to find out more about IABAC certified data science courses offered by DataMites. We'll keep you all posted for the upcoming events by email and social media channels, and looking forward to connecting with you all soon. Thank you all for attending today's session, and have a nice day. Bye-bye.